What's inside the SpaceX Starship? It is a stainless steel, fully reusable rocket created and built by the corporation SpaceX and launched into space in 2011. The rocket will be made up of two stages, the Super Heavy booster stage and the Starship spacecraft at the top of the rocket. It is possible that Starship will be the tallest and most powerful rocket ever constructed. Both stages use Raptor engines to burn liquid oxygen and methane in a controlled environment. The rocket may land on mechanical arms on the launch tower, while the spacecraft can use its flaps to control its descent. The booster may land on mechanical arms on the launch tower. In addition to fueling other Starships in orbit, the projected tanker type could also transport 100T, that's 220,000 pounds of cargo, to low Earth orbit, the Moon and Mars. Such a rocket was first proposed by SpaceX in 2005, with the design and name of the vehicle changing on a regular basis since then. In July of this year, Starhopper, a prototype vehicle with enlarged fins, demonstrated its ability to hover successfully. After 4 failed attempts by previous prototypes, the Starship SN-15 successfully flew to a distance of 10 kilometers, that's 6 miles, and landed there in May 2021. The first Starship rocket is scheduled to launch in 2022, according to plans announced in January 2022. The development of the rocket is iterative and gradual, with prototypes being tested and built as the project moves forward. However, detractors have pointed out that the project's unattainable milestones, environmental harm, and resident displacement have all been recognized. SpaceX intends to build launch sites at Starbase Kennedy Space Center and 2 offshore launch platforms as part of its expansion ambitions. In the near future, Starship may be used for a variety of missions, including delivering satellites and space probes, providing services to space travelers, and exploring the Moon through the Artemis program. Further into the future, the rocket may be used to transport people and cargo between areas on Earth, as well as to assist SpaceX in its goal of colonizing Mars. This degree of operation is only attainable as a result of the lower launch cost. Design: Starship is being developed to be a fully reusable orbital rocket with the goal of dramatically reducing launch costs. A single launch could send more than 100 tons or 220,000 pounds to low Earth orbit, so establishing the rocket as a super heavy lift launch vehicle in the official classification system. Depending on how it is built and powered, Starship may weigh up to 5,000 tons, that's 11 million pounds, be 9 meters broad and 120 meters high, making it taller than the Saturn V by 9 meters. In addition to the super heavy first stage or booster, the rocket will also have a Starship second stage or spaceship. Raptor and Raptor vacuum engines provide the power. The reusability of these rocket stages, as well as their stainless steel construction, has had an impact on later rockets such as the Terran R and Project Jarvis. The first rolls of stainless steel of the SAE 304L grade are used in the production of the Starship rocket. These rolls are unrolled, cut, and welded together along with the cut edge to form a cylinder-shaped structure. Each of these cylinders has a diameter of 9 meters or 30 feet, a height of 2 meters, and a mass of around 1,600 kilograms. The outer layer of the Starship spacecraft is constructed by stacking 17 of these cylinders and nose cones and welding them together along their edges. Domes are located inside the body, separating liquid methane and oxygen tanks that are under tremendous pressure. These domes are created by robots and welded together at a rate of 10 minutes per seam, according to the manufacturer. Following that, they are subjected to an X-ray examination. Raptor is a family of rocket engines that are utilized in the Starship, which is manufactured by SpaceX. In a full-flow staged combustion cycle, it combusts both liquid oxygen and methane at the same time. The entire family is made of a novel alloy that can withstand pressures of up to 300 bar inside the main combustion chamber. These engines are capable of firing many times, with their nozzles being kept cold by the surrounding running propellant, a process known as regenerative cooling. It is possible that the engine family may be mass-produced in the future at a cost of approximately $230,000 per engine and $100 per kilonewton. It is the only full-flow staged combustion cycle engine currently in production, and it is part of the Raptor family. Such an engine has been attempted in the past by Soviet Union and the United States, but neither product has ever been successfully deployed in combat. Generally speaking, a full-flow staged combustion cycle engine contains 2 pre-burners, each of which is coupled to its corresponding turbopumps. One of the pre-burners is fed with an oxygen-rich mixture, while the other is fed with a propellant-rich mixture, with each pre-burner combusting a small amount of fuel to drive the corresponding turbines in the same direction. The cycle subsequently feeds all of the gaseous propellant mixture into the combustion chamber, in contrast to the other engine cycles that squander some propellant during the combustion process. This boosts the engine's chamber pressure, allowing it to produce greater thrust while also being more efficient in overall operation. Methane was selected to be used for the Raptor engines for a variety of reasons, including the fact that it is potentially cheaper, does not accumulate soot, and can be created on Mars through the Sabatier reaction. It is necessary to run the engines at a 3.6:1 mass ratio of oxygen to methane, since combusting a stoichiometric mixture of 4:1 would cause them to overheat and fail. Carbon dioxide and water are present in the exhaust, with a trace quantity of carbon monoxide and nitric oxide present as well. At full strength, the plume reaches a length of approximately 65 meters, which is approximately 15 meters longer than the Starship spaceship. When several rocket engines are clustered together inside a rocket stage, the plumes from the inner engines do not immediately interact with the surrounding air, resulting in a plume that is far longer. Raptor is one of the several Raptor types that SpaceX builds. According to the manufacturer, the Raptor engine has a 1:34 ratio between the throat area and the exit region. Another is the Raptor vacuum, which is intended to be sent into space. With a nozzle extension composed of brazed steel tubes, it may increase the throat area to exit area ratio to 1:90 and the specific impulse of fuel efficiency to 380 seconds, resulting in increased performance. The Raptor 2 is the second generation of the Raptor family. Its engine has a thrust capacity of 2.3 mN, that's 530,000 lbf, and a particular impulse that has been lowered by 3 seconds. The design of the new Raptor generation is more straightforward than that of the previous generation. On a long-term basis, SpaceX intends to build 3 different versions of the Raptor engine: a sea-level optimized engine with gimbal thrust, a sea-level optimized engine without gimbal thrust, and a vacuum optimized engine without gimbal thrust. Booster with a lot of power. The Super Heavy rocket is a booster or initial stage of the rocket that is positioned at the bottom of the rocket. The booster stands 70 meters or 230 feet tall and can accommodate up to 33 Raptor engines that are optimized for operation at sea level. In comparison to the Saturn V, the engine cluster may be more than twice as powerful. The tanks of the booster can contain a total of 3600 T of propellant, which is made up of 2800 T of liquid oxygen and 800 T of liquid methane, respectively. Super Heavy's dry mass is predicted to be between 160 T and 200 T when not fueled by propellant. The tanks weigh 80 tons, the interstage between the booster and the Super Heavy weighs 20 tons, and the engines and mounts weigh a total of 52 tons. In addition, the booster is equipped with 4 grid fins, each of which has a mass of 3 tons. These grid fins are not uniformly spaced to allow for greater pitch control, and they can only spin in the direction of the roll axis. In some cases, they may be used to regulate the booster's descent and as a mounting point for a landing into the tower's mechanical arms. Despite the fact that capturing Super Heavy requires extreme precision, it may be possible to minimize the turnaround time after landing and enable more frequent launches in the future. It is possible that the booster will fire cold gas thrusters powered by evaporated propellant stored in internal tanks in order to regulate its direction. While the Super Heavy and the Starship are still joined in space, the booster is able to move its engines and detach from the other spacecraft. Thanks for watching this video. If you liked it, make sure to give us a thumbs up and subscribe to this channel for more amazing content.